Hello and welcome to Conceptual Physics at Delaware Tech, Chapter 27, Color. So we spent the last unit talking about the properties of light, so there's going to be a little bit of review, but in this section we're going to talk about color in our world and selective reflection. This is the colors that are reflected to our eyes. We'll talk about selective transmission. These are the colors that pass through some material. We'll talk about mixing colored lights, and then we'll talk about mixing colored pigments. And these behave almost the opposite of one another. And that is because the light we see from an object is the light reflected to us, not the light absorbed by that object. Whereas pigments will reflect a certain light and absorb certain other lights. Then we'll talk about a lot of questions you may have asked when you were a kid. And you may have gotten an answer that was correct, or you may have gotten something else. We'll talk about why the sky is blue, why sunsets are red, why clouds are white, and why water appears to be blue or greenish blue. So color is really our physiological experience. It's our perception of frequencies of light, of wavelengths of light. It's not necessarily a real thing. It's the way our brain interprets the frequencies of light that hit our eyes. So it's really in our eye and it's in our brain. It's in the brain of the beholder what colors we see and how we see them. So colors depend on the frequency of light. The receptors in our eyes respond to different frequencies of light, and therefore different wavelengths of light. If we have high frequencies, that's low wavelengths. If we have low frequencies, that's high wavelengths, long wavelengths. So the lowest frequency that we can see, the lowest frequency of visible light, is the red light. That has the lowest frequency, the shortest frequency, but also the longest wavelength. And if we go below red, we end up in light that we just can't see, the invisible infrared light. It's called infrared because infra literally means below. So it's below the red in terms of frequencies. It's lower frequency, it's less energy, it's a bigger wavelength, it's outside of our visible range. So our visible range of wavelengths, of frequencies and wavelengths, from the lowest frequency and highest wavelength would be red, and the highest frequency and the lowest wavelength would be violet. So the colors of the rainbow, and obviously there are millions of colors in between these. These just happen to be the ones we have English words for. So when people say, how many colors on the rainbow? Oh, it's 7. No, it's actually technically infinite. We just have words for 7 of them. But the colors that we think of are red, orange, yellow, green, blue, indigo, and violet. And we remember these with the mnemonic Roy G. Biv. It's a fake person's name, but if you look at all the letters, they match the 7 colors of the rainbow. And so the highest frequency of all of these is the violet light. We kind of group the blue, indigo, and violet all together as the high frequencies. These are the highest frequencies, the shortest wavelengths, but the high frequency also means they're the highest energy versions of these electromagnetic waves. If you go beyond that, if you go above the violet in frequency, beyond violet is the ultraviolet, because the prefix ultra actually is an ancient Latin word that just means beyond. So when you say ultraviolet, it literally means beyond violet, beyond what we can see of the visible range that ends in violet. Beyond that is the invisible ultraviolet, just like below the red is the infrared. That's the part we can't see either. All right, so let's look at the first question. What can the human eye see? A, infrared radiation, IR. B, ultraviolet radiation, UV. C, we can see both. D, we can't see either. Well, we just finished talking about it. We can't see either infrared or ultraviolet. The words literally say below the red. Red is part of the visible range, or above, beyond the violet. Those are outside of the rainbow of colors that we are able to see as human beings. So we can only detect the wavelengths that we refer to as the visible light spectrum. It's called the visible light spectrum because those are the only colors that are visible to us. There are other living organisms that can absolutely detect infrared or ultraviolet radiation. In fact, there are certain fish, there are bullfrogs, mosquitoes, maybe even vampire bats. There are a lot of different organisms, usually cold-blooded organisms, that can detect infrared radiation. Why mostly cold-blooded organisms? Because warm-blooded organisms, their own body heat would interfere with the detection of the infrared waves. Remember, infrared causes heat, so their own body heat would interfere with it. So there are very few, possibly none, depending on how you're counting it, warm-blooded animals that detect infrared. I know I said vampire bats, but it's questionable whether it's really seeing it or sensing it in another way. Ultraviolet light, on the other hand, there are a large number of organisms that can see ultraviolet light. Cats and dogs might be able to see it. There's some debate over that. Hedgehogs can see ultraviolet. Butterflies and certain bees and butterflies and beetles can see infrared light. Reindeer use infrared vision to look for lichen to eat. The sockeyed salmon use infrared vision to look for plankton and small fish. And scorpions actually fluoresce in the ultraviolet range, so they can use it to spot each other and spot other things as they're moving around. Interestingly enough, the goldfish and the mantis shrimp can actually detect infrared, what we call visible, and ultraviolet. They actually have very broad ranges of vision, color vision. And in fact, that's in part because goldfish, we have 3 color receptors, red, blue, and green. Goldfish have 4. Mantis shrimp have 12 different color receptors, plus another 4 that detect polarized light. So these 2 organisms have some of the most advanced eyes in the entire animal kingdom. All right, so selective reflection. This refers to the fact that when we look at an object and we see color, some objects will absorb light of some frequencies and reflect light of other frequencies. The ones we can see, the ones we actually notice, that is the color that we perceive. So objects that absorb all visible light, in other words, they don't reflect anything back to our eye, no light gets back to our eye, they appear black, absolutely black. The blackest things that we can look at are black because they absorb all visible light and none of it is reflected back to our eyes to perceive as color. So objects that can only reflect those frequencies that are present in the illuminating light. What does that mean? That means if you shine light on it that's white light, well, you have all the colors. So if the object has a color, that light will come back to you. But what if you shine light that's not all the colors? It's not white light that has all different colors. Maybe I shine a blue light on something that's green. Well, if something is green, the reason why it is green is because when light hits it, the green light of that will bounce back to our eyes. But if I'm shining pure blue light on an object, there is no green light to bounce back to our eyes, and the object will just appear black. So we see the colors of a rose by the light it reflects. So when we've got a red rose in this picture, that means all the other colors of the rainbow are absorbed. So orange, yellow, green, blue, indigo, violet, those are absorbed, but red is reflected back to our eye if we shine it with all colors of the rainbow. If we shine it with red, that'll be reflected back. If we shine it with a mix of light that has red, that'll be reflected, the red will be reflected back to our eyes, and we'll see red. If we shine it with something that has no red in it, so if we shine it with white light, there's red light in it, and it will reflect back to our eyes. But if we shine it with something that has no red in it, it'll look like a black rose to us. All right, so here's an exact example of that sort of thing. We have a red ball. And the first picture, picture A, this is just hitting it with normal white light. White light has all the colors of the rainbow, okay? So you shine white light on a red ball. The pigments that make the ball red, those are molecules that absorb all the colors of the rainbow except red. They don't like red. And it's kind of weird to think about that when you're looking at objects, and I'm wearing a red shirt. The pigments in my red shirt are molecules that absorb orange and yellow and blue and green and indigo and violet. They just don't absorb red. They reflect red back, and that's why you see a red shirt on me. That's why you see a red ball here. So if we just shine pure red light on it, yeah, we'll see red behind it because we're shining red light on the wall, on a white wall. But there is the red light that hits the ball is bounced off the ball, and some of it will reach our eyes. So we will still see it as a red ball. There is red light in red light, so that red light can bounce back to our eyes. But what if we shine it with green light, pure green light, has no red in it? There's nothing to bounce back to our eyes. So all of the green light is totally absorbed by the ball. You might light up the area around it with a green glow, but there's nothing bouncing off the ball to our eyes. That ball is only capable of bouncing red light off. And if you shine a pure green light, there is no red light to bounce back to our eyes. There is no light that bounce back, no visible light that will bounce back to our eyes, and therefore to us it appears black. Black is the absence of light. There is no light coming from the ball back to us. You get something similar if you use pigmented glass. So we've already learned that transparent glass that doesn't have any color added to it, all the visible light will go through it. It hits a particle, it's quickly absorbed, it's quickly released. Hits another particle, it's quickly absorbed, it's quickly released, and eventually the new photons will come out the other end that have exactly the same wavelengths as what we started. So if we shine white light on it, the red light will go through, the orange light, yellow, etc., all the way to the violet light. All of it will go through the glass. But what if we have blue glass? This is glass that has blue pigment molecules embedded in the glass. And these molecules are blue because they love to absorb every color of light except blue. So when light passes through the glass and we're looking on the other side, the only light that comes through is the light that is allowed by these pigments, and that is the blue light. It's the only thing it doesn't absorb. So the blue light will go through. It might be scattered too and reflected around, but only blue light can reach us. Only blue light can get through the glass. Every other color of the rainbow, of the visible light, is absorbed by this blue pigment in the glass. So we see it as blue. The color of the transparent object will depend on the color of the light that it allows through, that it does not absorb. So colored glass, like this blue glass, will absorb red and orange and yellow and green and violet and indigo, but it won't absorb blue. But those are all these other wavelengths of light. And if the light is absorbed in there, that energy has to go somewhere, and it goes to eventually warm up the glass. So colored glass will get warmer a lot faster than clear glass because there are things in there that are absorbing the light. It's not just letting the light through. Normal transparent glass only absorbs 2 to 4% of the light. But now we're absorbing the vast majority. Only one wavelength of light is getting through. One frequency of light is getting through, and those are the frequency and wavelengths that correspond to the color blue. Now, if you look at the sun, in our solar system, it produces a lot of light, and technically our sun is white. It looks yellow to us, and we'll talk about the reasons for that. But our sun is white because it's producing all colors of the rainbow. And this is a spectrum of the light produced by our sun. If you look on the y-axis is brightness, so it's how much light, and it's how much light of each frequency. And you can see by the colors in the visible range of what frequencies correspond to what color light. So our sun will produce some infrared light with low frequency and some ultraviolet light we definitely know about from suntans and sunburns and skin damage. It produces that ultraviolet light at high frequencies, but it also produces a lot of visible light. And as you can see, most of the light that the sun produces is visible light, and this is no coincidence. The sun produces this light. We and many of the organisms on this earth have evolved to be good at being able to see with our eyes the bulk of the light that the sun produces. If we were on another planet that had a different star that made a different range of frequencies of light, we might have evolved into creatures that have eyes that will detect a different range of light. But we have evolved to detect the light that is produced by our sun that illuminates everything around us. So that's what we see. We see the visible range because that is the best evolutionary solution for survival, to be able to see the light that is around us produced by the sun. So if you look at it, it's not even for all the visible light spectra or even for the ultraviolet and infrared. There's a peak, and it actually peaks somewhere around the yellow-green range. That's where you get the most intensity of light, from the yellow-green. But it's it covers the red, the orange, the yellow, the green, the blue, the indigo, the violet. It covers all of them with a little bit of infrared and a little bit of ultraviolet. So all of those wavelengths are produced by the sun. So we have organisms on Earth that can see infrared and some visible and ultraviolet. And like I mentioned, the goldfish and the mantis shrimp, they can actually see the whole range of light that's produced by the sun, or almost most of the range that's produced by the sun. So it gives them great evolutionary advantage. The sun produces all these wavelengths, and if you add, since we have a lot of each of the colors, they more or less add up to white, which is why our sun is actually white. Now, it appears to us as yellow. There's a reason for that, and we'll talk about that near the end of this unit. But it's actually a white star. And the receptors in our eye are really geared towards the red, the green, and the blue. That's where we see best. Those are the color receptors we have in the rods in the retina of our eyes. So we are particularly sensitive to kind of the center of that range, which would be that yellow-green area. That's what we see best, right in the center of the red, green, blue spectrum. So here are the three colors that our eyes have receptors for. So the red are the low frequencies, the high wavelengths. The blue are the high frequencies, the low wavelengths, and the green are intermediate. So these are the three color receptors we have in the eye. I mentioned the fish have 4, so they can expand their, goldfish have 4, they can expand their range. Manta have 12, and I'm sure they overlap and cover an even broader range. So the reason why we have evolved to have these 3 color receptors, red, green, and blue, it turns out that if you mix red, green, or blue light, pure red, pure green, pure blue, you can make pretty much all the colors of the rainbow by just combining different pairs or all 3 in different intensities. And this is why in TV sets and in computer screens we use what are called phosphors. These are chemicals that, when they're excited, will produce either blue light, green light, or green light, or red. Blue light, green light, or red light. And in combination, we can make any color, and that's why we have these full Technicolor screens on our computers and on our TVs using only 3 colors of light. Actually, I'm going to back up here and just point them out. So if you look at the red light and the blue light and the green light, if you add all 3 together, you will make white light. Okay, but if you only add the red and the green, you actually make yellow light. Now, this is definitely counterintuitive for anybody that learned with crayons. We learned that yellow and blue make green. That's for pigments. We are talking about light, because when you're looking at pigments, you're looking at what light is reflected back to you, as well as what light is absorbed by the pigments. But in the case of shining lights, you're just looking at the color light that you're shining, because that's what reflected back to you. We're not worried about absorbance. There is no absorbance in this case. So it confuses what you're definitely used to, and it takes a while to get used to this concept of these additive primary colors of light being the red, the green, and the blue. So if you add green and blue together, you get this lighter blue called cyan, and that's kind of a bluish green, but it's referred to as cyan. And if you mix red light and blue light together, you get magenta. And you'll notice those three mixed colors, magenta, yellow, and cyan, are the three pigments used in almost every color printer in the world right now. And we'll get to the reasons for that. So red, green, and blue light overlap to form A, red light, B, green light, C, blue light, D, white light. Well, we just finished saying those are the primary colors of light, what we call the additive colors of light. When you add them together, they become white light. And if you add any pair of them together, you get either yellow, magenta, or cyan, depending on the combination. You will get this color chart as well as another color chart in your reference handout that has your formulas. So you don't have to memorize it, but try to become familiar with it. So when you mix all three primary colors of visible light, these are what we call the additive colors of light, you'll get white light. All right. So when the color yellow is seen on your TV screen, remember you have phosphors on your TV screen that make the colors. The phosphors being activated on the screen are A, yellow, B, blue and red, C, green and yellow, D, red and green. Well, there are no yellow phosphors. Your only choices are red, blue, and green, the primary additive colors of light shown here. And you have these big circles of light, red, green, blue, and they overlap in different ways and make other colors. And as you can see, yellow is formed when you overlap red light with green light. So it's red and green. The phosphors will mimic the three photoreceptors of our eyes. So that's why we use those colors in TVs and computer screens, because that's the same receptor colors that we use in our own retinas. And as in our eyes, the combination of red and green phosphors will produce yellow to our eyes. We'll perceive it as yellow. A blue object will appear black when illuminated with A, blue light, B, cyan light, C, yellow light, D, magenta light. Okay, well, think about that. Any object will appear black if nothing comes back to our eyes. If no light is reflected back to our eyes. If it's a blue object, the only light that would be reflected to our eyes is blue light. But what if we shine it with something that has blue light? That'll get reflected back to us. So any light we shine on it that has mixed in with it blue light, we'll see an object as blue. Some of that blue light will come back and hit us in the eyes. But if we shine a light that has no blue in it, there's no blue light to bounce back to our eyes. So if we look at this, blue light clearly has blue light, it'll bounce back to our eyes. Cyan is a mix of blue and green light. So the blue light will bounce back to our eyes. The green won't, but the blue will. And magenta is a mixture of red and blue, looking at this chart here. So the red will be absorbed, but the blue part will reflect back to our eyes and we'll still see blue. But the yellow light is composed of red and green. There is no blue there. So if we shine yellow light, that's really shining a red and a green light together, but we're not shining any blue. So there's nothing to come back to our eyes. So yellow light will make it appear black. So any object will appear black if it's illuminated with a light that doesn't contain the color of that object. There's nothing to bounce back to our eyes. And yellow light is just made of red and green. There's no blue there. So a blue object can only appear blue if there's blue light that can bounce back to our eyes, and yellow doesn't have any, so it'll appear black. All right, so we talked a little bit about the primary colors. Let's talk a little bit more about mixing of these primary colors, and then something that's called subtractive primary colors. These are the colors of pigments. So let's first talk about the additive primary colors. These are the colors of light that are the primary colors, the red, the green, and the blue. If you mix red and blue, you get magenta. That kind of makes sense to our brain, similar to pigments. If we mix red and green, we get yellow. This makes no sense to anybody that's used to using crayons or paint or whatever to mix, but this is light. This is not pigments we're mixing. So you kind of just have to accept that red light plus green light makes a light that looks yellow to us. And blue and green makes cyan. This sort of makes sense to our brains, but not really. But again, this, you just have to accept this is what physically happens. There's no way around this. If you shine a green light and you overlap it with a blue light, the overlap will appear cyan. If you mix all three colors together, you will get white light. If you mix all three colors together and you have a little extra intensity of one of those colors, you'll get white light and the extra intensity of the, say if I added a lot of red and a little bit of green and a little bit of blue, well, the little bit of green, the little bit of blue, and the little bit of red will make white, but that leaves some more red, so it'll still appear red. All right, but we have these other primary colors called the subtractive primary colors, and these are the colors of pigments. These are the ones that might make more sense to you using crayons or paints or ink or whatever, mixing colors. And they're called subtractive because when you look at a pigment, it is absorbing some frequencies of light. It is subtracting them out, and you only get what it doesn't subtract out back to your eyes. So we use, if you look at the original list of colors, the additive primary colors, red, blue, and green, the secondary colors, the ones that are mixed from those three, are magenta, yellow, and cyan. Well, magenta, yellow, and cyan now become the primary colors of the subtractive colors, the subtractive primary colors. These are the pigment primary colors. And the reason for that is each one of those three, cyan, magenta, cyan, magenta, and yellow, each one of those will reflect its own color and absorb the remaining colors. But remember, yellow pigment is yellow because it is reflecting yellow light to our eyes. But yellow light is blue and green. So when you see the color yellow, that is because blue and green light is hitting your eye, your receptors in your eye, and the one color is not being reflected back is the one opposite the green on this diagram, blue. Blue is not part of it, so blue gets absorbed and the red and green reflected to your eyes, and you see them as yellow. If you look at cyan, its opposite is red. Red is the one color that's not reflected to your eyes with cyan. A cyan-colored object, cyan-colored ink, absorbs red and reflects both the blue and the green to your eye, and that's why you perceive it as cyan. You only get the non-red colors coming back at you, and that's what you see as cyan. Finally, with magenta, magenta is the subtractive color where green has been subtracted from the white light. So if you take green away from the white light, all you're left with is red and blue, and red and blue make magenta. So when you see a magenta colored shirt or dress or piece of paper or whatever, that is because you are being hit with blue and red light. Red and blue make magenta, and it is absorbing the green, the color opposite it. So you can look at either one of these color diagrams and see what color is opposite. That's the one that is not involved in that particular color. So if you add any two of the additive primary colors, red, green, blue, you will create a complement of the missing primary color. In other words, if I add red and blue together, I get magenta. That's the complement of the remaining primary color, green, right? So magenta is opposite of green. Now, what does that mean? Well, if I have an object like this white ball here, and I shine three colors of light on it, the three primary additive colors, blue light, a green light, and a red light, they're all shining from the bottom of the right diagram here. They're shining from the bottom at different angles. So the light in the back of the ball will overlap, but the light will also be blocked by the ball, depending on which light we're talking about, which angle we're talking about. So when we shine green light on a ball, the ball is still illuminated in the back of the ball by red light and blue light. But the green light is blocked because the ball's in the way of the green light. So if you look at the middle shadow, that's a magenta shadow. It's magenta because the red light shined in the back of the ball, and the blue light was shining in the back of the ball, but the green light was blocked by the ball. So red and blue light that is back there will make a shadow that is magenta. And if you look at each of the others, you get the same sort of deal. Cyan is opposite of red. So if you shine a red light on the ball and the other two lights are also shined, the light that gets behind the ball is the blue and the green, but not the red. So the shadow is a mixture of blue and green, but red has been subtracted out. So you can think of the ball as subtracting out one color of light depending on which shadow you look at. So the cyan shadow, that's cyan because blue and green light are hitting your eyes to make cyan, but the red light has been stopped by the ball. And then finally, the last combination, blue and yellow. So if you shine a blue light across the ball and the other two lights are shining behind the ball, the light behind the ball, the green and the red that still get behind the ball, they'll make a yellow shadow, but the blue light is blocked. So yellow is the color of white light where blue has been subtracted. Magenta is the color of white light where green has been subtracted. And cyan is the color of white light when red has been subtracted. And this is why they're called the subtractive primary colors, also known as the primary colors of pigments. So subtractive primary colors are going to be complementary to the additive primary colors. In other words, magenta is complementary to green, yellow is complementary to blue, cyan is complementary to red. The first ones I named were all the subtractive ones. The second ones I named were all the additive ones. And the reason why is if you were to add magenta and green together, well, magenta is red and blue, and green is just green. When you add them together, you get all three, and that's white. They're complementary because if you add the colors of light from each of those complementary pairs, magenta and green, or yellow and blue, or cyan and red, if we're talking about light hitting us, we end up adding all three of the primary additive colors, the red, green, and blue. So if we look at yellow and blue, yellow is a mix of red and green. And then we add blue to that, well, now we have all three, that's white light. And then the last example, cyan and red. Cyan is really a mix of blue and green light. We add red to it, we've got all three, that's white light as well. All right, so in the case of subtractive primaries, the magenta, the yellow, the cyan, this is what we use for color printing. So the additive primary colors are primary colors of light. On the other hand, the subtractive primary colors, your magenta, yellow, and cyan, these are the primary colors of pigments. They're the primary colors of ink in printers. So if you want to make blue color on your paper, you would mix cyan and magenta ink together. If you wanted to make green ink on your paper, you'd mix cyan and yellow ink together. And if you wanted to make red ink on your paper, you'd mix magenta and yellow together. Now, these don't quite make sense to us because we're so used to using the primary colors we learned in grade school of blue, red, and yellow instead of blue, red, and green for light, or magenta, yellow, and cyan for pigments. But this is what's actually used in printers. They are recognized as the primary colors of pigments and are referred to as the subtractive primary colors of light because these are made from subtracting one, absorbing one of the three main types of light, red, green, and blue, subtracting them by absorbing them and then reflecting the other two back to our eyes. All right, a red rose will not appear red when illuminated with red light, orange light, white light, cyan light. Well, remember, anything red will appear red because red light was available and it bounced off the object to our eyes. Well, we have an object that bounces red light back to our eyes. That's what makes it red. Anything red is because it reflects red and absorbs the other wavelengths. So you need light that has some red in it. Well, red light has red in it. Orange light has red in it. White light has all colors in it. But cyan light, look at this color diagram. Cyan light is made of green and blue. There is no red in cyan. And as a result, cyan containing no red to bounce back to our eyes, the red rose will appear as a black rose. So red, orange, and white each contain components of red light. There's red light to hit us. Cyan has no red light. It's just green and blue. And Therefore, the rose will appear black. All right. So, only 3 colors of ink plus black are used to print all color photographs or color prints on your printer. We use magenta, cyan, yellow, and cyan. We also use black ink to kind of enhance things, because otherwise we'd be dumping so much magenta and cyan and yellow and cyan together to make black. It just wouldn't be worth it. It'd be too expensive. So when you combine all 3 colors shown in D, you see all the colors, but it's hard to get black unless you're really pounding in a huge amount of pigment. So we usually add black to it in order to get the colors darkened to the level where they look natural in diagram F. Through sheets of these colors, if we had all 3 stacked together, a cyan sheet, a magenta sheet, and a yellow sheet, the light that goes through, all of the visible light is absorbed and it'll appear black. So in this diagram you see in the upper right, imagine these are transparencies that have different colors in them. Remember, cyan is cyan because it reflects a mixture of blue and green to us. And that means cyan color is that color because the only primary color it's absorbing is red. Whereas magenta is magenta because blue and red light is hitting our eyes. We see magenta. It is that color because the only color magenta objects are absorbing is green. And yellow objects are yellow because green and red light are hitting our receptors in our eyes. And the only color that is absorbed by a yellow object is blue. So when we have a mix of yellow and cyan sheets, all the frequencies except the little extra green are subtracted. So what does that mean? All right, let's talk about that. If we have a yellow sheet reflects red and green light to our eyes. That's why we see it as yellow. The only thing it absorbs is blue. So we have that sheet down and we're shining white light through it. So the only thing it's removing, the only thing a yellow sheet is subtracting out is blue light. And so it appears yellow to us. A cyan sheet reflects blue and green. That's why it looks cyan to us. The only color it's absorbing is red. So it's holding the red light back. So we have the yellow sheet holding the blue light back. We have the cyan sheet holding the red light back. Well, what's left? The 2 sheets reflect a combination of red and green and blue and green. But they absorb only blue and red. Well, if they only absorb blue and red, the only thing left to hit our eyes is green. Now, if you look at the combination of light that's being reflected, we have 4 things of light here: a red, a green, a blue, and another green. Well, if these are all in equal intensities, the red, the green, and the blue, one of the greens, the red and the blue, will combine to make white light. But there's still green light being reflected to our eyes because that's one that is not being absorbed completely by these 2 sheets. And as a result, when we have the yellow and cyan together, green is the only thing that gets reflected because the yellow is subtracting out blue, the cyan is subtracting out red. The only thing left is green to hit our eyes, and that's why it appears green when we mix a cyan ink with a yellow ink. The cyan ink is holding back the red, the yellow ink is holding back the blue, and the only thing left to hit our eyes is the green, and that's why it appears as green. So you can use various combinations of cyan, yellow, and magenta and make all the colors of the rainbow, all the colors of the spectrum. And if you look at this diagram in the bottom right, this is a diagram of what reflected light might hit you, the combinations of reflected light on the left, and you see various combinations of the rainbow, and then what your eyes will perceive that as. So if we look at the top one, it's the whole rainbow hitting your eyes. We perceive that as white light. If it's only red on the left here, well, that's the only color we see. If you go down 2 more steps, if the blue and purple are the only things hitting your eye, you'll see it as blue. We're not as good at seeing violet colors because our receptor is tuned mostly to blue. Yes, we see purples, we see violets, we see lavenders, but we would see them much more intensely if we had a receptor that was a little higher frequency than just blue. And if you have various combinations, it's frequently the middle of those combinations, that's the light that'll be predominant to you. So if you look at the, say, where it says yellow light here, Yellow light is listed over on the right where it says what you see, where it says yellow. And then you look on the left, you see there's a combination of red, orange, yellow, green light that's being reflected to your eyes. You'll notice the color of light that's not being reflected are the blues and violets. So when you take away blue from the primary colors of light, what you're left with is red and green make yellow. Yellow is kind of in the middle of that spectrum of red to green, and that's why we see it. And I'll leave it up to you to look at this table and kind of analyze it for yourself. So let's keep all of this in mind, and then we're going to switch gears and start looking at the questions that you probably asked as a small child. Why is the sky blue? Why is the sunset red? Why is water blue, etc.? And we're going to answer these questions, and they're a little more complicated than you might have imagined the answers to be, and some of the things you may have heard might not be correct either. So let's look at why the sky is blue. Well, the blue color is the result of what's called scattering. This is light that bounces off of molecules in the air and reaches our eyes. And it turns out there's a type of scattering called Rayleigh scattering. I won't quiz you on the name of the scattering, but you should know that it's light that hits molecules and bounces off, and then we see those frequencies of light. And it turns out that Rayleigh scattering there are a couple different kinds of scattering. Rayleigh scattering is scattering where you have the particle sizes, in other words, the molecules of nitrogen gas and oxygen gas are much, much smaller than the wavelengths of visible light that are hitting them. But Rayleigh scattering works better the smaller the wavelengths, the higher the frequency, the higher the energy, you get more and more scattering. So high frequency will scatter much more than low frequency. Well, remember, our high frequency light is our invisible ultraviolet, which we won't see anyway, but also the high end of our rainbow, our violets, our indigo, our blue, and to a lesser extent our green. And these are the ones that will interact most with the molecules of air, with the nitrogen and the oxygen in our air, and be scattered all over the place and re-emitted as scattered radiation across the sky that we will see. It'll hit our eyes. So when we look up in the sky, the light that in the sky that reaches us, there's all this different colors of light, but the light that gets bounced back down to us, to our eyes, tends to be more in the ultraviolet, the violet, and the blue range. Now, we don't see the ultraviolet, so that leaves the violet and the blue range. So the best scattering is at the highest frequencies. The red, orange, and yellow are scattered, but at a much, much lower level, so we barely notice those. So it's due to the selective scattering of light waves by the molecules. And if you have larger molecules, especially particulates in the air, or that are more than just molecules, they're whole chunks of things with enormous numbers of molecules in them, like dust and sand and pollen and smoke, things that get in the air all the time, these will start interacting even more and interact with even other wavelengths, so that even while the oxygen and the nitrogen favor scattering the UV and the violet and the blue and the little bit of the green light, you might get other scattering, and eventually it becomes, you see all the light scattering and your sky becomes whiter when you have all this dust and pollen and sand and smoke. But if it's just the clear sky, most of it will be blue that reaches us as we're looking at the sky with the sun up in the sky over here, and we're looking at the sky here. It'll look blue because that's the light that gets scattered down to our eyeballs. And that's because these gas particles resonate with these higher frequencies and they scatter them. We just don't see the UV because our eyes don't have detectors for UV. And that leaves the violet and the blue to actually hit our eyes. So why isn't the sky more violet? Well, there are three reasons why we don't see a purple sky. Number one, if you remember that chart of the light that the sun produces, it kind of favors the yellow, green in the middle, and then there's red and there's blue, but there's not a lot of violet and ultraviolet. There's enough ultraviolet to hurt us if we're out in the sun for a long period of time, but there's much less violet than there is blue, and then the most is in the yellow-green. So there's just less violet light to scatter to our eyes. The other thing is the violet light tends to scatter much higher up in the atmosphere, so not as much of it gets down to us. The bluer light tends to scatter in the lower atmosphere, and that we get to see. And then the third reason is we have three receptors for color in our eyes: the red for the low frequencies, the green for the mid frequencies, and the blue for the high frequencies. We don't have a direct violet receptor. Our blue will pick up violets, so we can see violets and purples that we see every day, but we don't have something that's centered on violet to really make them intense to the receptors in our eye and therefore be detected in our brain. So we just see a blue sky. If we were creatures from another planet that had a blue receptor and a purple receptor, our sky might look a little more purple than it is right now. But so because some of the blue light in this is scattered, so this is light from the sun, the sun's overhead, and the blue light, the sky, the air in the sky that we're looking up in the sides, that blue light is scattered towards our eye. But if we look at the sun itself, remember that blue light is scattered away from the sun. The sun is the source of the light. The blue light is scattered over to the sides. That's why we see the blue over here and the blue over here. But when we're looking at the sun, the blue has been scattered away from the sun. Well, what happens when you take white light of the sun? Remember, the sun has all colors of the rainbow in it. When you remove some of the blue, what is left? Yellow, the complementary color on those color diagrams I showed you. Remember, yellow is red and green light hitting us. So if we have white light and we take away the blue, what's left is red and green light together make a yellow sun. And that's why we perceive the sun as yellow, when in fact the sun is really a white star. So we have variations in the color of the sky, and I kind of already hinted when I talked about the pollen and the dust and the other things. If we have a really clear sky, it tends to be a deep blue color, maybe even a little violet in there that we can see. Even on a clear, humid day, it tends to be a nice, beautiful blue sky. But then we start putting in dust and smoke and particles and pollen and whatever is blowing through the air. These are much, much bigger particles than the nitrogen and the oxygen of the air. They're large. We might have larger molecules. We might have big particles that are much bigger in size, and they will scatter even lower frequencies. Why lower frequencies? Because lower frequency means bigger wavelengths that start matching closer to the size of these big particles. And now, instead of just scattering blue light and purple light and maybe an ultraviolet that we can't see, we start scattering lower frequencies: green light, yellow light, orange light, red light even. Well, what happens when we scatter all the colors of the rainbow? That means all of them are hitting our eyes when we're looking up at the sky. Well, what is the color that we perceive when we see all visible light colors? It's white light. So when we have a lot of stuff in the sky, a lot of dust and pollen and whatever, smoke, the sky appears whiter to us. It's less blue, and it starts taking on a whitish appearance. And after a heavy rainstorm, that rain will wash all the garbage that's in the air out. We have a much clearer atmosphere. Now we're back to just the simple nitrogen, oxygen, and trace gases in there. And then we end up with a nice deep blue sky again. All right, so white sky is evidence that the atmosphere contains A, predominantly small particles, B, predominantly large particles, C, a mixture of particle sizes, D, pollutants. Well, a white sky might mean pollutants, but in general it means we have a mixture of particle sizes. Remember, each different size particle will scatter different collections of colored light or even non-colored light that we can't see. So the smaller the particle, the smaller the range of wavelengths, which means the higher the frequency of it. So if we have small particles, small molecules like nitrogen and oxygen, then we'll only scatter the smallest wavelengths, the highest frequencies like ultraviolet, blue, and violet lights. But we start having bigger particles, dust and pollen and sand and whatever in the air, and you can get fine sand, by the way. There are photographs of giant sandstorms from the Sahara Desert blowing across the ocean. That gets in the air. But all these particles will start having their own collection of light to scatter. And the bigger the particle, the bigger the wavelength of light it will scatter. Bigger wavelength means smaller frequency. And then you'll end up with the whole spectrum of colors in the rainbow. So if you have all these different size particles in the air, you'll have all these different size wavelengths being scattered, all these different size frequencies being scattered, and if you get all of them in the rainbow, our sky looks white at that point by seeing all the wavelengths throughout the rainbows. All right, so why are sunsets red? Okay, we just talked about why a daytime sky looking up when the sun is over here and we're looking at the sky and we see it blue, because blue are the wavelengths that are hitting our eyes the best. Well, when we're at sunset, now the path that the sunlight is coming is a little different. If we're looking right above, there's just a thin layer of the atmosphere above us, between us and the sun. But when we're looking at sunset, the sun has set to a position. If you look at this diagram down at the bottom, you see the greatest path that the sunlight would travel through the atmosphere is at sunset. That's when the sun is coming straight along the horizon and the light is traveling through huge lengths of the Earth's atmosphere before it reaches our eye. Well, instead of the blue light being scattered towards us, if we're looking up in the air, now all the blue light, that light from the sun is coming towards us, and we're looking at the sun or towards the sun. The blue light is scattered, still scattered, but now it's scattered away from where we're looking. We're looking towards the sun. The blue light is scattered in every direction, mostly away from us. And as a result, we see what's left over after the blue light is scattered. We don't see much blue at all. What we see, what's left, is the other side of the rainbow, the reds, the orange, the yellows. And this is why at sunset, when the blue light is all scattered out of our field of view, that what we see are those warm colors, the reds, the orange, the yellow sunsets. And if we have particles in the air, we might see other colors as well, but those are the primary colors that we see. I don't mean primary colors, but those are the major colors we see at a sunset. So it's the same reason for seeing the blue sky, the yellow sun, and the red sunset. It's all because of scattering of blue and purple light. When we're looking up here at the sun, the blue is pushed away and we see the yellow sun. When we look over here, we look at the sky, we see the blue light that has been scattered down on us, and we're looking at sunset, we're looking at the sun. Again, the blue light has been removed, and now the whole sky, it's been removed as we're looking down, looking across the sky at the sun, and now the blue light is all scattered out of the way, and what we see are those reds and orange and yellows of a classic sunset. All right, a variety of sunset colors is evidence for a variety of A, elements in the sun, B, apparent atmospheric thickness, C, atmospheric particles, D, primary colors. Well, each color we see is the result of scattering of different wavelengths of light. So we have a variety of atmospheric particles. The smallest particles, the actual air molecules, nitrogen gas and oxygen gas, they will scatter the smallest wavelengths, the highest frequencies of light. Bigger particles like the dust, the pollen, the sand, the smoke, whatever, they will scatter bigger wavelengths of light, which are lower frequencies. And if you have enough mixture, you'll get all these different colors appearing because you have a variety of sizes, scattering a variety of sizes of wavelengths, which means a variety of frequencies of light. If molecules in the sky scattered orange light, right, they scatter blue light, instead of blue, sunsets would be what? Orange, yellow, green, or blue. Well, let's think about this. So if we're looking up at the sky during the day, we're not talking about sunset just yet. We're looking up, and if the orange light was scattered, that would be what we'd see. We'd see an orange sky during the day. And the orange light would kind of be removed from the sun, and we'd see what's left over after you remove the orange light. But if you looked at the sunset, the orange light is removed. The orange light is scattered by this thick atmosphere that the sunlight's coming through. Well, what's left over after you pull out the orange light? Well, we haven't talked about orange per se, but let's think about what orange would be. If you remove orange light, it's not going to be orange. It's probably not going to be yellow. Blue is the closest thing we have to the opposite of orange. And so the sunset would appear blue and the sky would appear orange. It's like everything is reversed. All right, so clouds. Clouds are typically white. Why are they white? Well, let's think about what clouds are made out of. They're made of clusters of water droplets. You may have heard some memes that are out there now, and these are true, that the average cloud weighs a little over 1,000,000 pounds. It's 1,000,000 pounds of water vapor and water droplets floating around up there. It's huge. The density isn't that great because it's spread over an enormous volume of space, but it's made of water droplets, and you have tiny water droplets and you have bigger water droplets, and eventually if the water droplets get big enough, it starts raining. But let's think about the size of these water droplets, okay? So we already learned that with gas molecules in the air, the nitrogen and oxygen, we get Rayleigh scattering. They'll scatter high frequencies like the ultraviolet, which we don't see, the violet, which we kind of see, and the blue, which we see really well. And that's why the sky looks blue and the sun looks yellow and the sunsets look red. But water droplets, they're much bigger. They're much bigger than single molecules. Water droplets are made of trillions, quadrillions, or more particles of water. So they're much, much bigger. And now we get a different kind of scattering called Mie scattering, M-I-E. This is actually named after, I believe, Gustav Mie. Rayleigh scattering was named after Lord Rayleigh, an English scientist, and Mie scattering, Gustav Mie, was a German scientist. So Mie scattering, this is scattering that is not particular about wavelength. Rayleigh scattering goes for high frequencies more than low frequencies, so you get more blue scattering than red scattering. But Mie scattering is a different kind that scatters everything equally. It has no preference for wavelength or frequency of light, and as a result, these big water particles have this Mie scattering, and they scatter all colors equally. And remember, what happens when all colors of light hit us simultaneously? We perceive that as white, and that's why we have white clouds. So why do we have darker clouds? Well, darker clouds, they have bigger particles, bigger clusters of droplets, especially when it's about to storm. The water particles get bigger and bigger right before a storm. Well, the particles, yeah, they still reflect white light, but remember, while water transmits most of the light, goes through, a little bit of light is absorbed by the water. And the more water you have up there with the bigger particles, the more light is absorbed. Well, what happens when light is absorbed? Things look darker. We have less light coming down to us. Yes, it might be a mixture of light that would make them appear white, but there's less of this white light hitting us, so they just appear less than white, gray, or even black clouds sometimes when they're really about to storm, when the droplets are huge and there's so much internal reflection of light up there that it doesn't get back down to our eyes, and everything looks darker. And that's why storm clouds look dark to us. And eventually the drops are so big, they start falling out of the clouds, and that's when we get a storm. All right, so why is water blue? Why is it greenish blue? Okay, well, there are a couple reasons, but let's talk about the one that affects most water, oceans and the seas, and even really deep rivers, or even deep lakes, and sometimes even deep swimming pools. Why do they appear blue? Well, it turns out, while we think of water as perfectly transparent, all the visible light goes through, that's mostly true. But it turns out they absorb a little bit of red light. Well, what happens when you pull the red light out? What's the other two colors of primary colors of light left? Well, the rest is blue and green. So red light is reduced to about a quarter of its brightness by the time you get down 15 meters. 15 meters is roughly about 48, 50 feet deep. By the time you're there, enough red light has been absorbed, about a quarter of the original amount of red light has been absorbed. The water starts looking like the other colors that haven't been absorbed, the blue and the green. And by the time you're down 30 meters, there's barely any red light down there. So the light that comes up to us that we see looks bluish green. And that's why oceans are blue-green or blue. That's why seas are that way. That's why deep pools, really deep pools, they have to be really deep lakes look that beautiful blue-green color. And it's because they absorb a little bit of red and they actually reflect a little bit of blue and green. So water actually has a tiny, tiny bit of color to it, but nothing we'd notice if we're just looking at bottles of water or even a giant jug of water. So when much of the red light is removed, the remaining blue and green can reach us from the deep depths, from relatively deep depths, and we see this mixture of blue-green. Remember, blue and green light makes cyan. Now, if you go deep enough, if you go too deep, all the light is eventually absorbed and nothing reaches us. So by the time you're down deep in the water, the sunlight doesn't even come down, so the water becomes pitch black at certain depths. So that absolutely happens. But other than that, if you're looking above, when you're looking at the sunlight coming in and bouncing back at our eyes, a lot of the red light's absorbed, and that's why oceans are blue-green. It's not because of the reflection from the sky, and the sky is not because of the reflection from the water. There's another type of blue-green color that happens when you have things like glacier-fed lakes. And this is a classic effect of glacier-fed lakes. The Canadian Rockies are loaded with these spectacular lakes that are the result of the melting of glaciers. And the color we see is still partly due to the absorption we had, but it's also due to another kind of scattering. So these lakes are fed by glaciers. So the glaciers melt, but it's not pure water coming off the glaciers. The glaciers have been dragging across land and mountains and flat ground and trees and whatever, and over millions of years sometimes, certainly thousands of years, and they grind up everything underneath them so that when they finally melt, they've got all these fine particles inside of them, silt and what we call rock flour. This is like dust that's from rocks being ground down to a fine powder. We also call it glacial flour. It's kind of an interesting term. And these particles are so small that they don't settle very quick in the water. They don't settle down to the bottom of the lake or whatever it is. They kind of get suspended in the water and take a long time to settle. Well, because they're kind of suspended in there in the water and not fully settling to the bottom, they will scatter light on their own. And it turns out that these particles also will absorb the highest frequencies, which are the shortest wavelengths of light, like your violets and your indigos. Those will be absorbed. And then the water, we already know, absorbs a little bit of the red and the orange and the yellow, the lowest frequencies of visible light, the longest wavelengths. Well, if we have the big particles absorbing the indigos and the violets, and we have the water absorbing the red, orange, yellow, the only thing left is the middle colors, the blues and the greens. And that's what gets scattered by these particles to our eyes. Well, light scatters from these tiny particles. We see blues and greens together. That's kind of a cyan. It's kind of a turquoise. And these lakes have this spectacular, vivid turquoise color as a result. This bluish green, gorgeous color that you really only see in mountain lakes that are fed by glaciers with the silt and sand and rock dust that the glaciers feed into these lakes. So remember, color that we see, this is our perception by our brain using the receptors in our eyes. It might be different for other creatures. Every creature will see color differently. And if we were to someday meet creatures from another world, they would perceive different colors differently than we do. It's our own perception based on the frequencies of light and based on what we can detect and how our brain interprets that information. And with that, we'll stop here.